Okay, in this second video on Chapter 5, we started out talking about transformations using matrices. So, for example, like a translation, if you slide something or move it or add something to it, that's the not technical approach to the definition of that. But a translation technically is any translation of the XY plane. You can represent it by the functional form of this. So here's your functional form. You would say f of xy, so the new one, equals the old x plus h and then the old y plus k. So if you're going to do that and you're going to do it as a matrix, this is what it would look like. Here's your old x, here's what you're adding to each component, and here's your new. So a lot of times they'll call the XY matrix just X. They'll call the HK matrix just H. And then the resultant would be H prime. So just notational information. Okay, if you stretch or shrink something parallel to an axis, the transformation is this. So this is going to stretch it 2 times on parallel to the x-axis. In terms of a matrix, if you had a matrix that's going to stretch only the x, it'll look like this. So notice, if you multiply this row times this column, you get 2x. And then this row times this column, you get y. So y is unchanged. So that's how you would represent it in a matrix. Okay, and the last thing, this form. So what's happening here is you're doing 2 things to x's and y's. You are taking a multiple, so this matrix right here, the A matrix, is multiplying things. Here's your X matrix, and we call it the X matrix even though it has X and Y. And then after you're done multiplying, you're also going to add. And again, that's going to be the H matrix, even though it includes H and K. So this operation of multiplication, matrix multiplication, followed by matrix addition, will give us our new X's and Y's, and we'll call that matrix capital X prime. That's the new X matrix that contains X's and Y's. Okay, so that's kind of a connection between transformations and this new material about matrices. Okay, we're going to step back and go and talk about determinants, which is just back to matrices. Okay, a determinant is kind of a unique footprint of a matrix. So it's just product minus product. So you're doing cross multiplication. This product right here minus this product right here will give you a number. Okay, a determinant is a number. When we actually put numbers in, the number we're getting for this determinant of this matrix is 4. So I could either tell you to take a determinant by putting DET in front of the matrix, or I could instead make my matrix lines into straight lines. That's saying take that determinant. So this determinant, I could say it this way, or I could say it this way, -1, 2, 5. But the end result is I'm going to say 15 minus a minus 2, because I did the cross products, this product minus this product. Since it's a minus of a minus, I end up getting 17. Okay, so let's move on. The next page, we're going to be relating a matrix to an area problem. So this answers the question, when will I ever use this? And you can use determinants to get areas of shapes. So here's an example of using a determinant to get an area of a rectangle. So the key is you have to have one corner at the origin to have this work. So the area of rectangle ABCD can be determined using matrices if it has this left corner. So set up matrix A. So look what matrix A is composed of. Here are the coordinates at the furthest x point. Here are the coordinates at the furthest y point. Okay, so 6, 0, coordinates of D, and 0, 4 are the coordinates of B. So the absolute value of that determinant, and we know the determinant is the product, is the area. So if I were just to figure out length times width, I would say this is a 6 by 4. I would get 24 square units from my area. My matrix, find the determinant, gives me the exact same value. The key is area has to be positive, so you're going to take the absolute value of your determinant. In this case, our determinant was positive anyway, so we didn't need to worry about the sign. But should your sign be negative, you will take the absolute value of that sign, and that will give you the area of your rectangle. In the textbook, they do this with a parallelogram. That also has a corner at 0, 0. You may want to just look at that if you want to see another example of this kind of information. Okay, we're going to go on to one other thing with matrices, minors, and cofactors, because they're going to help us get the determinant of a larger matrix. Okay, on this lab, we're going to learn two new words, minors and cofactors. Okay, you get a minor by breaking up a larger matrix and then taking its derivative, or its determinant. So for example, here we have a 3 by 3 matrix. If I want to find M minor of row 1, column 1, what that means is I eliminate the row 1 and the column 1, and this becomes my new matrix. I am now going to take the determinant of that. So 2 times 2 is 4. So let me just make sure I've done this correctly. Yeah, hang on one second. Okay, so it looks like I lost my head here. If I have 2704, that determinant is going to be 2 times 4, which is 8, minus 0. So this should be 8, and I will fix that on my PowerPoint slide that I'll post. So you will not see that 14 there when you print out your copy. Okay, look at the next one. So I'm going to erase what I have here. And now if we want to instead, and we'll change color, let's instead find minor 1, 2. That means that we're going to get rid of row 1, and get rid of column 2. Okay, so we're kind of eliminating the T. So what matrix do we have? We have a 0, 7, 1, 4, and 0 times 4 is 0, minus 7 times 1, so minus 7 is my determinant. Okay, and let's do the last one. If we want to figure out the minor of M1, 3, let me erase this again. Change color, and this says eliminate row 1. Row 1 is here, and column 3. So here's the matrix 0, 2, 1, 0. Find the determinant. 0 times 0 is 0. And 2 times 1 is 2. And since it's 0 minus 2, your determinant is minus 2. So you can think of these as mini determinants. Mini determinants are the minors. Okay, so next thing. What if I want to figure out a cofactor? So a cofactor is a multiple times the minor. So remember, the minor is a determinant. So if I want to know cofactor A11, so let's go back. Cofactor A11, I'm going to erase that. Okay, cofactor A11. So that means I need minor M11. that value is going to be 8, not 14. Okay, so I'm going to change that also on my original copy. Now, what's my multiplier? Well, my multiplier is -1 raised to the 1 plus 1. So that's -1 times -1, +1. So my A11 is 8. And I'm going to show you how to use these in a second. But you need to know how to get your minors and then how to get your cofactors. Okay, so you want to know what all of these things are. Okay, so we want to calculate the determinant of a 3 by 3. And I am going to ask you to be able to do this. So you have two ways that you can do it. The first way uses cofactors, which are the aij's and the minors. So this is our equation. To get the determinant of A, what I'm going to do is I'm going to take the sum of these products from 1 to n, where n is the size of your matrix. Okay, so if your matrix is 3 by 3, then you're going to find the j that goes up to 3. Okay, so for example, let's just say that my matrix was indeed 3 by 3. What I'm going to do is I'm going to take my A11 times my M11. Okay, now what happens to that multiplier? This -1 became positive, so that's positive. Okay, now if I do the A12, 1 plus 2 is odd, so that negative is going to stay negative, and that is why that's negative. Okay, so then the next one, A13, 1 plus 3 is 4. 4 is positive. This raised to a positive power will be positive, and that's why that's an addition. So if you do A11 times M11 minus A12 times M12 plus A13 times M13, you will have the determinant. So that's one way. Okay, so this is one way to do it. Here is the second way, and many people like this way better. Okay, so what you do is you have this initial matrix. You then copy all of those elements so that your matrix looks twice as big. To then get your determinant, what you're going to do is you're going to multiply. You have to figure out, you're going to have this, so very carefully, I have this, and I have this. Okay, so I'm going to have the first product of the three terms plus the second product of the three terms plus the third product of the three terms. Then what you do next is you're going to subtract each of these. Get that product and subtract it. Get that product and subtract it. Get this product and subtract it. So you should only have a couple of letters that you haven't touched. Okay, and those are here and here. So if you know you're not going to touch those, it's going to be easier for you to get your diagonals. Okay, so the red was here, here, and here. Okay, so when, just a little word of caution. When you do this product, if that product itself is negative and you are subtracting it, it will end up being an addition. Okay, so just be careful about that. Okay, so we're gonna do one of these, but maybe not right this minute. Will we? No. We're gonna hold off and we'll do it in a couple of more slides. Okay, so how do we calculate this inverse? Okay, so this seems like a goofy rule, but it really does work very well. So if you have a 2 by 2, to find the inverse of a 2 by 2, this is what you're going to do. If you have, so I started out with this matrix. It was 4, 7, 2, 6. Okay. To get its inverse, this is what we're going to do. We're going to swap the positions A and D. So that's the 4 and the 6. So swap them out. They become 6 and 4. Then you're going to put negatives in front of B and C. So that means since these were positive, they are now both negative. If one was negative already, it would become positive. Okay, so you're basically going to reverse the signs. That is, that is the inverse. Okay, that's part of the inverse. That's the first step. Then the next step is to divide every single term in here gets divided by the determinant. And how do we get the determinant? 4 times 6, 24, minus 7 times 2, minus 14, gives me 10. So every single term is going to be divided by 10. Okay, this example showed this with decimals. I would prefer that you do it with fractions. So this would be 6 tenths, negative 7 tenths, negative 2 tenths, and you can reduce these if you wish, positive 4 tenths. That's your resultant matrix. Okay? So how do I know if it's correct? They're telling us down here to verify it. If you multiply your initial matrix by your inverse matrix, you will get back your identity matrix. That's how you know you are correct. Okay, so then next page we're going to talk about how you can possibly use matrices to solve word problems. Okay, so here's kind of an interesting application. It says a group took a trip on a bus, and they're spending $3 per child and $3.20 per adult for a total of $118.40. Then they also took a train, and the train cost $3.50 per child and $3.60 per adult for a total of $135.20. Okay, so they want to know, can you do this as a matrix problem? And can we figure out, given this information, how many adults we have and how many children we have? So this is what we're going to do. Here is your matrix A. So actually, this is your matrix X. So this is X, this is A, and this is your cost. So we'll call this maybe your B, okay? So look what's happening. If you take this matrix, which is a horizontal matrix, it's a row matrix, multiply x1 times 3 and x2 times 3.2, you'll get 118.4. Okay, then take that same row matrix and multiply it by the second column of the second matrix, and you'll get 135.2. But how do we figure out how to get x by itself? So you have to get rid of the a. So if this was an algebra problem, we would just divide by both sides by a, and you'd be all set. But we cannot divide by matrices. So what we're going to do instead, we would say xa equals b, multiply this by a to the negative 1, multiply this by a to the negative 1. We know this gives me the identity matrix. So that returns my x value. And my x value, my x matrix, is the child-adult component matrix. So this equals that. And if I multiply these two matrices together, the B and the inverse A matrix, I will know how many adults I have. Okay, so we're going to continue this in the next page so you can see what we're building towards. And we're going to get an answer for our x's. Okay, so here's what we want to do. First off, we're going to need to get the inverse for A. So how do we get that? So you're going to flip this position with this position, and there they did that. And then you're going to negate Keep them in their spot, but just negate them, those two. Then what you're going to do is you're going to figure out your determinant of the original matrix, which is 3 times 3.6 minus 3.5 times 3.2, and divide every single term in this in-between matrix by that determinant. This is a to the negative 1. Here was your B, which was your prices of the tickets. Here is your A negative 1. Row, column, doing that math gets us 16 and 22. So what is 16 and 22? 16 is the number of children and 22 is the number of adults. So you can use matrices to solve these kind of simultaneous problems. Okay, so do inverses always exist? And the answer is no. Okay, so an inverse may not exist for a couple of reasons. First off, you can only take inverses of square matrices. That means that they have to have the same number of rows and columns. So that's one condition. The second condition, since you are dividing by the determinant, if you find that you have a 0 as a determinant, you can never divide by 0. So that's going to eliminate the fact that, eliminate the possibility of an inverse existing in that case. So an inverse, such a matrix, is singular, which only happens when the determinant is 0. Okay, so if you're told you have a singular matrix, there's going to be no determinant of it. The determinant will be 0. So there is going to be a determinant. It'll be 0. You cannot use 0 as a divisor. Therefore, you cannot find an inverse of a matrix that is singular. Okay? Okay, so I'm going to talk about calculations in just a second. Okay, so you can do many calculations on your calculator. I have showed you how to do everything by hand because in terms of understanding the concept, that's how you understand the concept. Secondarily, most of your classes will not all have graphing calculators that can do matrices. So therefore, your students are not going to learn them that way. But I'm going to say a couple of things about this. If you have a graphing calculator, why don't you take it out right now? And I want to show you where the matrix button is. So if you turn your graphing calculator on and you hit second, so to get to a matrix, you're going to hit the second button, and then you're going to hit the button that says this, x to the negative 1, and you see the word matrix there. So if you say second x to the negative 1, you see names, math, added across the top, and then you have all kinds of options, A through whatever, for matrices. So if I want to make a matrix, I would then put my cursor across the top and say edit. Then press 1 and you can build your matrix that way. Okay, so we're going to do this when I see you again in class. But in terms of what you need to show me in terms of your work, you've got to do this by hand. Inverses. Once you have a matrix, you can then use that x to the negative 1 key to get your inverse. You can add matrices as well on the calculator, and you can multiply by scalars. So there are many things that we can do with the graphing calculator, all of which I can show you, but it's important that you understand the basics of it this way. Okay, systems of equations is an outstanding application of matrices. Okay, if you think about systems, that's something that many grade levels will use, and you'll also use them in high school and college and beyond. So here are 3 equations, 1, 2, 3. And I've lined them up so that my x, y, and z are in the same order. Okay, that's important. Okay, you can build your first matrix, we'll call it the A matrix right here, by taking off the coefficients of your x, y's, and z's. Your next matrix, which we're going to call the X matrix, is a column matrix, and it consists of X, Y, and Z elements. Just those variables, because I want to solve for the variables. Then that's going to equal your last matrix, which we'll call the B, which are all the answers here. Okay, so how do we do this work? This is exactly like the problem we just did with the bus and the train. You have AX equals B. You can't divide by A, so you're going to multiply by the inverse. Now, you have to think about how you're doing it. You have to do it so that it conforms. Okay, so you're going to put it in front of the B, because my A is a 3 by 3, and my B is a 3 by 1. I can't put it behind the B because it will not conform. But if I do X equals A to the negative 1 times B, look what I'm getting. My X's will be a 3 by 1 matrix. My A to the negative 1, which is my inverse matrix, which I get by taking the inverse of the A matrix, and there's a whole procedure for that. My A to the negative 1 is going to be a 3 by 3, and my B is a 3 by 1. So these conform. So my answer will indeed be a 3 by 3. Okay, so you can then get a matrix back, which gives you all three of your answers right away, which is a wonderful thing. Okay, so systems of equations is a great application of matrices. Okay, we will not do much with this information, but I thought it was kind of an interesting little fun fact. So isometry is a transformation that retains the original shape of the object being transformed. A matrix A is said to be orthogonal, so that's a vocab word, which means at a right angle. If it's transposed, remember that's when you just switch the rows and the columns, is equal to its inverse. Okay, if your transpose equals your inverse, then the matrix is orthogonal. Okay, so a little fun fact there. Okay, another little interesting facts. If something is a proper rotation, it maintains the orientation of the original shape. So the proper rotation is where x prime equals a times x, and where the determinant of a is 1. If it's improper, then the determinant of a is going to be negative 1, and this is an orientation reversing operation. If you have a rotation plus a transformation, that's what you would have. Okay, we're not going to really do anything with this, but it's addressed in the book, so I thought I would mention it here. The next section, 5.6, isometries and complex numbers, that is important for our discussions, and we will be doing things with that, and we'll cover that on the next page. Okay, a complex number has a real part and an imaginary part. And I, if you think back to Algebra 2, I is the square root of negative 1. If a number is purely imaginary, that happens if it doesn't have an a component, and that happens when a is 0. If a number is purely real, that happens if b is 0. Okay, what you can do is you can add apples and oranges. So you add and subtract complex numbers by adding or subtracting their like parts. So for example, if I have 5 plus 2i added to 2 plus 7i, to add those two, I would get 7 plus 9i. I cannot combine that any further. Okay, when you multiply complex numbers, you FOIL them, and you never leave an I squared in your answer. So, for example, if I have 2 plus 3i times 2 minus 5i. Foiling it, okay? The first is 2 times 2, that's 4. the outer 2 times negative 5, which is negative 10i. Okay, you do combine things when you multiply. The inner 2 times 3i, which is positive 6i. And the last, so the L in FOIL, is 3 times negative 5, both with i's. So that's negative 15i squared. That has to go. Okay, combine these guys together. So far I have 4 minus 10i plus 6i, so that's minus 4i. Now, I squared is equal to negative 1. So negative 1 times negative 15 is positive 15. So the end result is going to be 19 minus 4i. Okay, so whenever you have an I squared, when you square I, it becomes a real number. Okay, that real number is negative 1. So that negative 1 will always flip that sign. Okay, remember, you can never leave an I squared in your answer. Okay, we have one more slide, and that deals with conjugate pairs, another important concept. Okay, so if you're going to find the conjugate of a complex number, all you do is this. Here's your complex number. Here's your complex number. The conjugate has a different sign here. Okay, so if I had 7 plus 3i, my conjugate would be 7 minus 3i. Okay? Now the reason why the conjugate is important is because you can't leave I squares in your answer, and you can't leave a complex number in the denominator. So the way you get rid of it is by multiplying by the conjugate pair over itself. The reason why you can do that is because this is just a fancy 1, and you can always multiply by 1. Nothing changes. It's an identity multiplication. So let's do that multiplication. 7a minus 7bi, since I have no numbers. Okay, look what happens in the bottom. If you have a plus bi times a minus bi, you get a squared. So I'm going to FOIL it. First, a squared, outer, negative abi, that was outer, inner, positive abi. You see how those middle terms are going to cancel? Last is going to be negative b squared I squared. Okay, these cancel. This is a negative 1, which flips that sign. And so this denominator now becomes a real denominator, and it's a squared plus b squared, and that's what I have. Okay, so that ends this chapter. I know it's a very long chapter, and you have vectors, you have matrices, you have just a lot of material in here, so you may need to go back and go over it again. I'm going to go through, there is an activity as well, and I'm going to post that, and I'm going to post my annotated answers to that as well. And I may even do a video to go along with that.